Good morning, everybody. Welcome to our session on network virtualization. My name is Murari Sridharan, and this is Yushun Wang. We're from the Windows Core Networking team. If you're here because of the misprinted pamphlet, there's a different talk, which is 422, and the title is swapped. Okay, when we set out to build Windows Server 8, we wanted to make sure that it's easy for customers to build multi-tenant clouds, both public and private clouds, large and small, and to do so in a way that's cost-effective for them. We also wanted our platform to be manageable and extensible such that our partner ecosystem can innovate around us and help complete the virtualization story. Here's what we have on our agenda today. We're going to introduce Hyper V Network Virtualization. We'll show you how to use it to build multi-tenant clouds. Windows is all about our partner ecosystem. We will tell you the requirements we have of the ecosystem, and we'll also discuss a lot of partner opportunities here. At the end, we hope to show you that you can use network virtualization and get the most of your investments that you've made in your data center today. We're also going to show you partner opportunities for you to enhance and make your services and your hardware aware of network virtualization and multi-tenancy. And if you're an ISV, we are also going to talk about the extensibility that we have built in the platform that's going to help you build rich multi-tenant services and also management software for this product. Okay, the most common complaint that we hear from our customers is that their data center is underutilized. And the underutilization comes because there are certain things that prevent capacity from being easily consumed, consolidated, and used. As a result, more often than not, the server capacity is over-provisioned. If you have an over-provisioned data center and you're underutilizing your resources, then it's not cost-effective, so your return on investment is pretty poor. We'll try to understand the problems that constitute underutilization in the data center. So at the outset, the problem is one of resource fragmentation, right? So take the spanning tree protocol for instance, right? It's a layer 2 protocol that's used to eliminate loops. Now, when you eliminate loops, you also eliminate a lot of useful paths, and that's wasted capacity. So good links that you've paid for can no longer be used to eliminate congestion in your network or to just get more bandwidth from your network. Now, the physical aspects of this problem are being solved in both the IEEE and the IETF, and there's a lot of interesting work going on with standardization efforts like Trill that are trying to address that problem. But it is a problem today, and it is one of the causes of one of the things that causes resource fragmentation in your network. The fact that these links are eliminated means that your network is highly oversubscribed. Now, on the server side, we over-provision for capacity. On the network side, it's oversubscribed. So you have both the problems. Now, the fragmentation problem is sort of exacerbated by the use of these things called virtual LANs or VLANs. So VLANs are primarily a construct for broadcast isolation, and they're used to sort of divide up servers to limit packet storms and for the control plane traffic to be isolated, right? Let's understand a little bit more about how VLANs work. So the typical deployment for VLANs, the way the networks get segmented is you take a network, you carve it up into really small pieces, and you assign one subnet per VLAN, right? Now, there's only so many servers that you can put in each of these VLANs. The reason is at some point, the broadcast traffic overhead starts to dominate, and it doesn't really scale. So what you end up with is a lot of very small layer 2 networks in your data center. Now, how many such networks can you have? Theoretically, this is limited by the size of the VLAN ID, which is a 12-bit identifier. So that gives you about 4K tags that you can use. Now, if you try to use all of these tags concurrently, then the actual usable number of tags is dependent on the switch capability, right? So as I'm going to show you on the right-hand side, this is typically how the VLAN segmentation happens. You have 3 services, red, green, and blue. They are split into 2 different racks. And as you can see, the green and the blue services span both the racks. And for the communication to happen, the VLAN tags, corresponding VLAN tags, have to be configured on the aggregation switch, right? And the number of such tags you can have, as I said, is limited by the VLAN ID and the capability of the switch. Okay. A side effect of this problem, the side effect of the segmentation that I just talked about, is the fact that a lot of workload assignment or VM assignment in your network is largely static. The reason is you take any server, the server's location on the LAN determines the network address that it gets, right? Now, if you try to migrate workloads, first of all, you have to go reconfigure the VLAN tags in your network. But let's say you do end up migrating the network, migrating the workloads. What happens is you have to go reconfigure your network for connectivity to continue to work. And this process is inefficient. And I'm going to show you an example of what happens if you try to make this largely static data center appear to be dynamic. So it's the same example as before. I just have 3 racks, 4 switches. Again, there are 3 services, red, green, and blue, right? And let's say that the current assignment looks as follows. Now, the guy that's running the red service comes to you and says, I need to expand capacity. Now, there is capacity. So there's capacity in rack 2, for instance. So the operator says, OK, I'll give you some server capacity. Then he has to go and configure the VLAN tags on the switches. Okay? So far, so good. Then the service says, I need to expand some more, right? Well, we can expand some more. There is capacity in this 3rd rack, which is all the way on the other side of the data center. And now I have to configure VLAN tags on all the 4 switches, right? Now, even if you automate this process, even if this process is automated, it is cumbersome and it's often error prone. We keep reading about these service outages that happen, that takes out public services for long periods of time, and more often than not, the cost for this is just misconfiguration. So we showed you some reasons why data centers are over-provisioned, underutilized, resulting in a low return on investment. You bring in multi-tenancy, the problem is much, much worse. Okay? To motivate this, let's take an example. Let's say you're a public cloud service provider, and you're trying to onboard a bunch of tenants. And I'm using the word tenant here not simply to apply to public clouds. The word tenant actually equally applies to private enterprise clouds. That's because if I'm if I'm an enterprise data center trying to build a private cloud, then all my business divisions, my different organizations, all these guys are tenants because they all have SLAs that I need to meet. They don't want one division's services causing outages in somebody else's network. So the word tenant is equally applies to public and private, and the solution equally applies to public and private. Okay, so the hoster has a few options. He has a bunch of these guys to accommodate. He could either go, give them some dedicated servers and dedicated network, but that's not really going to be cost effective for him. For it to be cost effective for the cloud service provider, or for that matter, the enterprise the operator, he needs to be able to take all these guys and put them on a shared infrastructure. Now, once you put them on the shared infrastructure, you are back to the same problem of how do you isolate these tenants? How do you isolate the traffic? Then you're back to using VLANs. But only now, the fact that you have 4K VLANs is not enough when multi-tenancy comes into the picture. Even if somehow you can accommodate the VLAN tag pressure today, it's not going to scale. At some point, you're going to run out of tags, and that VLAN space needs to expand. But more importantly, for it to be cost effective for this cloud service provider, he needs to be able to take these networks, put them wherever there is capacity in his network, right? Otherwise, it's not going to be a cost effective operation for him. So this brings us to our vision for the data center. We believe that for data centers to be cost effective, you need to be able to operate your resources at very high capacity. In the sense, very high utilization. You want high utilization of both server capacity and network capacity. Now, for you to be able to efficiently use this capacity, you should be able to consume it no matter where it is available in the network. So wherever there's capacity, you should be able to expand, and then when you're done, you should be able to contract. So this is the vision that we have for data center for data centers of the future, which is you should be able to take any service, put it in any server, and it can be in any cloud. Now, what we have tried to do with Windows Server 8 is we have built a platform that helps you realize this vision. Now, before I proceed further, I want to show you how Windows Server 8 helps you achieve this vision by inviting Yushin to show you a demo of how you can move your network to the cloud.
Okay, so while I switch over to the demo system, we already explained a little bit of the problems and challenges in networks in the data center. But let's face it, we can build the most efficient data center in the world, but if customers are not on board, the cloud is not going anywhere. So what I'm going to show here is that let's see what the challenges the customer face when they move to the cloud and how Windows Server 8 with network virtualization can make it easy to onboard. So what I have here is that on the screen, I have a Contoso website, a Contoso social gaming website. So like any growing companies, at some point, Contoso has to determine whether I should expand my infrastructure to meet the increasing demand, or I can go to the cloud. The challenge is, how do I go to the cloud? Do I need to reconfigure my VMs, changing my network addresses? How about my firewall policies? And how do I connect from my corporate network to the cloud network, right? So for the demo here, we're going to move this Contoso web server. Right now, it's running in the Contoso network from the corporate network to the cloud, and show you how on the cloud side we can make it easy to manage and easy to onboard. So for the demo, I'm going to simply shut down the Contoso website. Like I'm going to pause it. So I'm closing the the browser and open it again just so you can see that later on we are actually connecting to the web server in the cloud. So once I stop the service, how do I move to the cloud? To move to the cloud, you can simply take the VHD, upload your VHD to the hoster, and on the hoster side, which is what I'm going to show here, you take the VHD, import the VHD, and with network virtualization, you can run the VHD as is without changing the VM's IP addresses or their network configuration, so that your policy, your firewall, your line of business application don't need to change. And that's what I'm going to do. So I have already, on the hoster side, I have imported the Contoso web server here, the HC web. I'm going to run a PowerShell script to provision the network virtualization and routing policies for this particular VM and tenant, and then I'll bring up the VM. So basically, the script, this is a PowerShell script. What it's doing is provision the network virtualization and routing policy, and in the end, it'll bring up the web server. But remember that this web server is now up and running. But for Contoso, how do I connect to this web server? I need secure connection so that I can manage my web server, or I have lined up business application running between my core and the cloud. And so the next step is Server 8 actually has inbox cross-premise connectivity built in. So you can actually establish secure site-to-site IPsec VPN tunnels very easily between your core to the cloud, and that's what we are going to do next. So what we have here is that we have a Server 8 VM running in the cloud, and another Server 8 VM running in the Contoso network. These two VMs will be the site-to-site VPN tunnel endpoint. And because they are running Server 8, we're simply going to run another PowerShell script on the Contoso's edge. This PowerShell script will bring up the secure tunnel. Oops, let me actually type it. So this is actually a very simple script. What it does is it creates a VPN tunnel, specify the secret, which is actually ABC, your password, and then bring up the secure tunnel between the cloud and the Contoso website. So now that the VPN is up and running, let's see if we can connect to the web server again. So the first time this runs actually takes a little bit because of the the Internet Key Exchange, IPsec Key Exchange protocol is actually taking place, and the VPN tunnel is getting established for the first time. So if this doesn't come up in a second, I'll probably start it again. But what's happening underneath is that I have the client sitting in the Contoso network, and then I have the server now actually onboarded and moved to the cloud. So let's see if the web server, so the web server is up and running, and I'm going to close the browser and start the browser again. Yes, it's probably hitting a lot of demo traffic with all the other sessions and demos going on. Okay, so while this is not coming up and running, I'm going to do another really geeky trick. So I'm going to ping, let's see, 10.0.0.1. Okay, so I can actually ping the corporate. That's actually the domain controller and the DNS server on the corp side. But let me try this again, and if not, we'll move on. So I can actually establish the cloud connectivity, but the web page is actually not coming up.
Can you ping the web server?
Yes, I can actually ping the web server.
Right.
Oh, actually, that's a good idea. Let's
Just
ping
show
the
the
web
ping.
server. Yes, so I can ping the web server, but the web server is not cooperating. Okay,
Why don't you do a trace route and show them that it's actually going through?
Okay, yeah, that's a good idea. Since we have a very targeted crowd anyway, so. So originally, when this is running in the corp, it's actually 2 hops, which we didn't show. And then now it's running in the cloud, it's actually 1 more hop because it's actually traversing through the VPN tunnel going to the other end. But unfortunately, the web server is not up. Okay, yeah, let's move on. So what we have demonstrated here is that we actually, this is it. Yeah, just like that. Yay, finally. Okay, so what we just did is basically we take a web server and we move it from the Contoso corporate network to the cloud. And then we established a site-to-site VPN tunnel between Contoso and the cloud and the cloud. Without changing the web server's IP addresses. So this is still 10.0.1.3, so we can access this. Now, once we have this up and running, let's switch to the hoster side. So for hoster, maintenance and consolidations are 2 big things that every operator has to deal with. What I'm going to demonstrate next is to move this Contoso web server, right now running in the cloud, from one network to another network in the data center without changing the VM's IP, without changing the web server's IP addresses while the server is up and running. And that's what I'm going to do now. So once again, from the PowerShell script, we're actually going to start the line migration and update the mappings. We can do this because network virtualization, as Murari will be explaining, actually maps the VM's IP addresses, the customer IP addresses, to a different hoster IP address on the wire. So when we move this VM to another network, we simply need to allocate a different IP address for that network on the wire, and then we update the mapping to every host with Contoso VMs. And you can see that the line migration is complete. We actually move from 157.0.1.111 to 2.222. And this has nothing to do with the 10. Address that the customer VM is using, and the whole thing is transparent to the customer. So let's see if we can still bring up the web server. Hopefully this time will be a little bit faster than last time, but let's see. As far as the customer goes, he's still accessing exactly the same DNS name. And then if the server comes up, we hope it should, and you will see that it's exactly the same web server that's actually running on the cloud. So the implication here is that now you can actually take the customer VM and move it anywhere in the cloud without disrupting the customer service, although the service is a little bit slow today for the demo. So the implication here is that if I can do that, I have the flexibility to actually take my rack down for maintenance, or I can consolidate, I can load balance my VM without worrying about changing the VM setting or even touching my network setting. So we're doing all this without actually changing the Contoso network. So I don't think this is coming up in time. So I'm going to switch back to the PowerPoint.
Yep. Okay.
Yep. Okay. So this is basically what we just did. So we take the Contoso web server, and we're onboarding the web server to the cloud. And as you can see, we onboard the web server. The customer web server is still keeping the same address, while underneath, the virtualization map it to a different IP address. So when we move to a different IP address, which I'm not showing here, basically it'll just map to 2.222, and then we update the mapping on the other host so that the host know where to route this packet to. So This is really a hybrid cloud scenario, as in you have the private cloud, you have the public cloud, and they are communicating with each other for onboarding, for communication, and such. So for enterprises, what it means is that now moving to the cloud can be seamless. You can move to the cloud, don't change your address, don't change your policy. And we preserve the host setting, preserve the network configuration, what you already have. And on the hoster side, you can see that it's actually very easy to onboard. All those PowerShell scripts are very simple. We will provide a sample. You can actually write those PowerShell scripts yourself. And we have flexible VM placement, so I can take the customer VM and spread it anywhere in the data center as long as I have IP connectivity. And finally, as Murari will be showing you, we increase the scalability, so now the hoster can actually manage a large amount of tenants, a huge number of tenants and VMs. So let me turn it back to Murari to explain how this works.
Thank you, Yushin. So that showed you how we can seamlessly onboard customers, and hopefully this product, Windows Server 8 is going to make cloud adoption really easy. Okay, let's dig into Hyper V Network Virtualization. So we all know and understand server virtualization, right? Server virtualization, basically you take multiple virtual servers and put them on a physical server, and they get the illusion that each VM gets the illusion that it's running on a dedicated physical server, right? Network virtualization is essentially the same concept, but instead of servers, you take multiple virtual networks and then run them on the physical topology. And each virtual network has the illusion that it's actually running on a dedicated fabric, right? The construct of the network virtualization is actually very powerful. So I want to explain a little bit about what you can do once you virtualize the network, right? As I said earlier, a server's location in the LAN determines its IP address. And with virtualization, with network virtualization, we are decoupling that. So we are able to provide you location-independent addressing, and we do that by virtualizing the IP address. That means you could take a workload, move it to any server anywhere in your data in your network, and it retains its IP address, right? That location independence is a very key concept that comes with network virtualization. Now, once you provide this virtual overlay, it lets you create arbitrary topologies on top of the physical fabric. So you could create layer 2, layer 3, whatever you want over any physical network. It's very important to note that this technology will work on any network, right? All we are expecting is bidirectional IP connectivity. Unicast for the most part, and if you want to support broadcast and multicast, we also expect the network to support multicast on the physical network. But other than that, you could take any physical network, for instance, a hierarchical 3-tier network, or if you're building these class or 2-level factory networks which provide you full bisection bandwidth, any of that, or even a large layer 2, with technologies like Trill, this concept of network virtualization will work on all those physical networks. Now, the other important thing to note is your virtual network can now not only span multiple physical subnets, it can also span multiple sites or multiple data centers. Okay, so it's important to understand how we virtualize the IP address, right? Now, to do this, we use two techniques in Windows Server 8. One is called generic routing encapsulation, and the other one is called IP address rewrite. So let's start with generic routing encapsulation. So GRE, or generic routing encapsulation, is actually an IETF standard. What it lets you do is it lets you, as Yushin was explaining, there are two concepts to understand here. One is a provider address, and the other one is a customer address. Provider address is actually uniquely routable on the physical network, and customer address is what the tenant brings with him. So you would expect that there is a lot of overlap between the customer address space, but the provider address space is unique for that network. Now, in this example, I'm going to show you that there are two servers. Each of them has a provider address that is uniquely routable. In this case, it's 192.168.2.22 and 192.168.5.55. Now, using this one address per host, I could accommodate multiple tenants, and each of these tenants can come with whatever customer address space they want. And in this example, as you can see, there is full overlap between the two tenants. There's a red tenant and there's a blue tenant. They happen to use the same private address space, in this case 10.1.1.11 and 10.1.1.12. And they are in fact located on the same server. So let's look at how communication will happen between, when these red tenants try to talk to each other and the green tenants try to talk to each other. When a packet comes out, it needs to be encapsulated, right? The address to be used for encapsulation is the provider address that's assigned to that host. Now, once you encapsulate the packet, the source address is, as you can see, 192.168.2.2, and the destination is the 5.55. Now, there is no problem in routing this packet because that 192 address is completely routable in the fabric. But once you route, is it okay? Okay. So as I said, the 192 address is uniquely routable, so there's no problem getting the packet to the destination server. But the destination server has a problem. It decapsulates the packet, and the inner packet has a destination of 10.1.1.12, and you don't know which one to send it to, because you have two tenants who have the same IP address. Now, this brings us to the concept of tenant network ID. Now, at a very, very conceptual level, tenant network ID is very similar to the VLAN ID, only that it's 24 bits. Using a 24-bit tenant network ID, you can support 16 million logical networks, which we think is more than sufficient. So there's no tag pressure there. But the really important thing to understand is this tenant ID can be embedded in the packet in the wire, right? Now, GRE provides a key extension in the header, which is a 32-bit field, and of which we're using 24 bits. And you can put this, the unique tenant ID into that. Now, what is a tenant ID? A tenant ID uniquely maps to a particular tenant's particular virtual subnet. So every packet in the wire carries an identification that you can use to do really cool things, as we'll talk about later. But in this case, the way the destination is going to differentiate the tenant is by using the tenant ID. The green guy has a tenant ID of 20, and the red has a tenant ID of 30, and that's how he's going to disambiguate and give the packets out. Now, so that's how the thing completes. Now, GRE allows us to do a one-to-n provider customer address mapping. That means I can use only one provider address, and I can have n customer addresses that are behind that. And it's not just one-to-n, it also lets you do m-to-n kind of mapping, right? You could have m physical addresses mapping n customer addresses, and it has a very useful, it provides a very useful use case, as I'm going to show you right now. Anytime you do any encapsulation, you have to worry about performance. You have to worry about MTU, you have to worry about performance in the host, you have to worry about performance in the network. Now, anytime you do any encapsulation, the first thing that happens is it's going to break a whole bunch of offloads, stateless offloads in the host server, right? It breaks things like LSO, checksum, receive-side scaling, receive-side coalescing, VMQ, a whole bunch of things break. And this is where we are engaging with IHVs, and we really encourage all the IHVs that provide these stateless offload capabilities to become GRE aware. That's how you get back the performance that you lose if you do encapsulation. And the second aspect is performance in the network. Now, as I said, multiple PAs can be mapped to multiple CAs, so it gives you an M-to-N mapping. This M-to-N mapping is actually very useful because it lets you have enough entropy in the packet if you want to do things like equal cost multipathing in the network. Now, ECMP, or equal cost multipathing, is basically a concept that's used in the switches to sort of distribute load so that no one link is congested. The way they do this is by computing a hash, and using the hash, which is unique to a flow, they decide what is the upstream link to take. Now, if you put only one IP address and there are n number of customer addresses behind that, then one of the problems is you lose a bit of entropy if you just look at the outer header, right? So again, there is both an opportunity here, which is we would love the hardware vendors to both inspect the packet. You inspect the packet by processing GRE and being able to do ECMP. And even if you cannot do that, there is an interim solution, which is for traffic that is heavy use of network, you can assign unique provider addresses to them. That is how you get entropy back, and that is how you can still get ECMP to work. Now, one of the big advantages of using GRE is the reduced burden on the network infrastructure. Now, server virtualization has actually increased the burden on the network infrastructure. Here is how that happens, right? So earlier, before the servers were virtualized, a top-of-the-rack switch would have a bunch of servers in the back, and the top of the rack switch would be aware of the MAC addresses of all the servers that it's serving to. And people designed the switches based on some size, right? I think it's anywhere from 16 to 64K. Now, if you start to bring a lot of VMs and put on these physical servers, let's say you put 32, 64, 128 VMs, now suddenly the MAC table starts to explode in these top-of-the-rack switches. Now, if you want more memory, that means a more expensive switch. So server virtualization has, in fact, increased the burden on the network. Now, by using GRE, we are getting some of that scalability back because you don't have to use a unique address for every tenant, right? That's the advantage of GRE. The last point here is, if you want deep multi-tenancy integration, you have to enhance your hardware, because any of these new technologies is going to put in things like tenant network ID in the packet, and for you to process and do interesting stuff with that, you have to enhance your hardware. So no matter what tunneling mechanism you pick, we believe that there is some hardware work required to take advantage of those services. Now, we were very cognizant of the fact that there is a performance implication in the short term, while the ecosystem adapts and provides, provides solutions that fills these gaps, right? Till you get NICs that can parse GRE and get back your stateless offloads, you still want to deploy network virtualization. For this, we came up with a pretty simple way of achieving it, and we are calling it address rewrite. Address rewrite is essentially just a static NAT. All we are doing is, instead of a one-to-n mapping that GRE provides, address rewrite is a one-to-one mapping. So for every customer address, there is a unique provider address. Now, you do lose some of the scalability that I discussed with GRE, but it's immediately deployable. The reason is there is no encapsulation, which means you don't have to sacrifice performance. You can get all your stateless offloads to work. You can get ECMP to work because there's enough entropy in the packet. And let's take an example of how this is going to work, right? It's the same example as before, but instead of one provider address, I have two provider addresses, one for each tenant. So the red guy on the source side is going to use the 2.22, and the green on the source is going to use 2.23. Now, the packet on the wire is we essentially rewrite the source and the destination address to correspond to where you need to route it to. Again, the 192 address is routable. On the receiving side, there is no ambiguity because it's a one-to-one mapping. So when you receive a packet on a certain provider address, you already know what customer it belongs to. So as a result, you don't have to put the tenant ID anywhere in the packet, right? Now, this is extremely useful because it lets you deploy network virtualization using Windows Server 8 today and get a lot of the benefits, while we wait for the ecosystem to adapt around any encapsulation mechanism that we provide, specifically GRE. So let me summarize. So we believe that GRE is the right approach for deep multi-tenancy integration with network virtualization. It's a standards-based protocol that we chose. The encapsulation overhead is fairly small compared to a bunch of other encapsulations we evaluated. And because it allows you to have few IP addresses per host, it gives you back a lot of the scalability that you lost when you virtualized your data center in the first place. And the entire Ethernet packet is encapsulated in an IP frame, and because of that, the full MAC address, the explicit tenant ID, everything is in the packet. So you could build a lot of rich services like traffic analysis, metering, control using GRE. And GRE is also the right approach for if you want to deploy V6 in your IPv6 in your tenants. If you want to onboard tenants that come with their own IPv6 addresses, GRE is the way to go because IPv6 generates a lot of temporary addresses. It also auto-generates addresses. So every time your customer generates an address, you don't want to go to the provider and ask him for a physical address, right? So the provider's already given you a physical address in the host. You can generate as many addresses as you want and continue to work. So GRE will let you do IPv6 in a much more scalable way. But then there is rewrite. Rewrite lets you deploy network virtualization today. You don't need to upgrade anything. No NICs, no switches, nothing needs to change, and you can get all the advantages of network virtualization. Of course, because we are doing a static NAT, all the restrictions that typically come with a NAT come with this. Only certain kind of protocols will be used, but we still believe that there is a lot of value and a lot of customers will actually use IP rewrite. The most important point is this is not really an either-or solution, right? For Windows Server 8, we will leverage both. Now, the platform is quite capable of supporting any combination. So you could say, to go to these set of addresses, use rewrite. To go to the other set of addresses, use GRE. Any such combination will work. And we're going to let the customers choose how they want to deploy this. OK, I'm very happy to announce the availability of this informational RFC, which we submitted yesterday. It's co-authored by a lot of leading industry players. This is talking about the GRE data plane. So this is basically a sort of a call to action for everybody, which is please come join the GRE ecosystem. There's a lot more work to be done here, and we would love for more partners. We'd love to onboard more partners into the GRE ecosystem. At the end of my talk, I will provide you a link for the RFC. We would love feedback on that, and come talk to us if you want to learn more about that. So here's the call to action, right? There is a lot of partner opportunity here. If you're a NIC vendor, we'd like you to implement GRE-compatible hardware offloads. If you're a switch vendor, we'd like you to use the tenant network ID information for both additional entropy in ECMP, or to do QoS, or to do ACLs, because the packet is now carrying an identification that gives you both the tenant and the virtual subnet. If you're an appliance vendor of any kind, we want you to build GRE-aware multi-tenant products. And one of the most important things for ISVs here is there's management software that can be built around this network virtualization solution, and the control plane can be multi-tenancy aware. OK, let's talk about the next aspect. So we spoke about how we virtualize the address. That gave us a whole bunch of properties. But because we are relying on a software construct for a VLAN, we have to talk about how isolation happens, because VLAN is used for not just for traffic management, it's also used for security isolation and performance isolation. So we'll talk about how we do the isolation in software. I hope a lot of you attended the Hyper V extensible switch talk yesterday. Now, in conjunction with the extensible switch and the network virtualization module, the isolation is provided in software in the end host. There are a lot of advantages in doing it in the end host, right? One is, as part of the port configuration, the switch already knows about all the ACLs that it needs to apply. So when you migrate VMs, the properties moves along with it, so that no matter where the VM is located, the isolation continues to happen. So take, for example, you had two services running on two different servers, and you had some hardware ACLs that you had applied that prevented them from talking to each other. Now, let's say you live migrate this and put both the services on the same host. You don't want to lose the ACLing. You want to retain the ACLing. Now, instead of having to go and touch a whole bunch of network devices to do the ACLing, because the hypervisor switch is going to do the ACLing for you, it means that the ACLing works no matter where the workload is, and you don't have to reconfigure your network. The second point is, because we are updating the end host, any misconfiguration is going to be isolated to a bunch of hosts at best, instead of causing broad outage in your network if you try to touch the network, right? So it's going to be isolated to a host or a few hosts. And the third and most important point is the extensible switch provides very rich functionality to build both forwarding extensions, monitoring, metering, a whole bunch of things. You can build firewall appliances, as we talked about in the yesterday's talk on switch extension. Now, because the tenant network ID is going to be available to these extensions, we want you to make all of these services that you're building multi-tenancy aware. We'll show you a demo of how the software isolation works.
OK, so let me switch over to the demo setup again. OK, so as you can see, we designed two demos just so in case that the web server actually shows up maybe like additional 20 seconds later. So this is, in our last demo, we actually onboarded the web server of Contoso from their corporate network to the cloud. So when we talk about all this goodness for Hyper V Network Virtualization, but what does that mean for the customers? I'm Contoso. I have a simple question. I'm bringing my IP address to the cloud. What happens if another customer actually are using the same IP address in the cloud? Would I see their traffic? That's fine. I mean, I want to see other people's traffic. But the problem is, would they see my traffic? Would the traffic cross-stream? What does it mean to have two different companies on the same cloud using the same IP address? So we have explained a little bit of how this works, but I'm just going to simply show you what this means to the customers. So for this particular demo, we actually onboarded another customer. So we actually migrated the Contoso web from host 2 to host 3. But here we have another web server for it's Northwest Trader. So we onboarded this before this demo just to show you what it means to be a multi-tenant. So you can see that in the Contoso client, the server IP address, let me scroll out a little bit. You can see that the Contoso, the client itself is on the corporate side, 10.0.0.3, and the web server IP address is 10.0.1.3, right now running in the cloud. So from the trader client, I'm going to open the web browser and point to exactly the same IP addresses as my web server. And let's see what it shows up. So as you can see, again, the client IP is also 10.0.0.3, while the server IP is 10.0.1.3. Because of the isolation and the virtualization mapping, traffic on the wire actually has no ambiguity. We know the blue client always goes to the blue page, and the trader, the red client, goes to the red web page. So let me switch back and basically show you what this what the setup actually looks like. So So in the beginning, there are two corporate networks. You have Contoso, we have the trader. So in the demo, what we did is we onboard the Contoso to the cloud. We onboard the web server to the cloud. So you see it's keeping its 10.0.1.3 IP addresses. And we have cross-premise connectivity from Contoso to the cloud. So what I didn't show, I only showed the result is we have onboarded another trader web server to the cloud using exactly the same IP address, 10.0.1.3 on the red web server. But because network virtualization maps it to different IP address and with tenant network ID, we can clearly distinguish between the trader packets and the Contoso packet. So you send it out, they will actually, the host, the hypervisor knows where to send the packet, and on the receiving end, we know for sure that which VM we should be giving these packets to. There's no cross-stream, there's no ambiguity. And this is how network isolation, network virtualization also enforces isolation guarantee in a multi-tenant environment. And that's the demo. Back to Murari.
Thank you. Let's talk about typical deployment and the whole management of the network virtualization, Hyper V network virtualization. So we want to show you a typical deployment. This is going to be true for in your data centers today, which is we expect that there will be some communication that is going cross-premise. So in this case, you might have a VPN gateway, you might have direct access or some other way to connect cross-prem. Then there's a whole bunch of infrastructure that you're accessing, which is Active Directory, DHCP, DNS, or you're going back to your SQL database, or there's a storage cluster that you're trying to hit. Now, as you can see, if you try to virtualize inside this network, now, if you use IP rewrite, then most of this will continue to work. But as I said, for better multi-tenancy integration, we want people to do encapsulation and GRE. So once you start to do GRE, then you can start to see that you need to bridge these worlds, because overnight, all your hardware is not going to just become GRE aware, right? So as a result, there is a lot of opportunity here to sort of fill the gaps in this typical deployment. Here's the call to action there, which is we'd like you to build GRE gateways that are cross-prem, that bridges public and private cloud. We'd like you to build appliances to move from virtualized to non-virtualized world, especially storage, because we don't want somebody's paid a lot of money to get very low latency and very high throughput. Just because you virtualized, you don't want to tell them that, oh, now there is a software gateway on the path that's going to do decapsulation. That's a bad idea, right? Instead, what would be good is if storage vendors augment their hardware to make sure that they understand GRE. Then it becomes not just a gateway functionality that's embedded in that product. Your product also becomes multi-tenancy aware, because today the concept of multi-tenancy is not built into a lot of physical appliances. You could also build just a standalone gateway that brings multi-tenancy to your data center without upgrading much of the other hardware, right? That's another possible hardware play here, which is go build a multi-tenancy capable appliance that's performant, that you can put in between a virtualized and the non-virtualized world. So if you're trying to hit some DNS appliance that you bought a long time back, which just works fine, you don't want to upgrade it, or nobody wants to upgrade that to be multi-tenancy aware, you could always put this hardware gateway in the middle. But more importantly, we want to vendors to think about this functionality as augmenting what you already have. You already are processing, you already know how to process UDP, TCP. You're probably, some hardware is also capable of, processing GRE. So we want you to build the gateway functionality into all of these appliances, top-of-the-rack switches, storage appliances, load balancers, routers, you name it, right? Or as I said, you can build a standalone appliance. So that's the hardware angle of it. Let's look at the software play for the ISVs. The platform is actually pretty rich in terms of the management primitives that we provide. First of all, everything that we talked about today is remotely manageable through WMI and PowerShell. And we provide a whole bunch of public APIs that you can use to configure query policy. You can understand packet drops that happen because of ACLs. You can also, we provide a notification channel through which you could dynamically update policy whenever workloads migrate. And we provide a whole bunch of logs for diagnostics and auditing. This basically means you could, this basically means that you can go build management software by taking advantage of all of these APIs and build a control plane that's multi-tenancy aware. And there is a lot of innovation that's possible in terms of policy distribution. So we'd really like for people to come talk to us about these APIs so that you can look at how to build management software around this. So to summarize, there are three key things that virtualization provides you. The first is flexible placement. By decoupling the physical infrastructure from the tenant's network, we will let you consume and use capacity no matter where it is in the network. This is going to be very powerful for people to run their data centers cost effectively. And remember, running your data center cost effectively is not just a cost problem, there is a huge competitive advantage. Today, there are a lot of large cloud service providers that operate and are extremely profitable, primarily because they have a very, very dynamic data center that they run. The second thing is you can administer VMs separately from the network, which means that just because you are moving workloads, so let's say I'm a server admin, I can move workloads using familiar tools like WMI, PowerShell, or my favorite management software. I don't need to understand VLANs. I don't need to go talk to the network admin, wait for some time, file a ticket, and all of those things, right? What I want to be able to do is go place my VMs wherever I want. Now, the network admin should be only focusing on capacity and performance in the network. So you want the network admin to configure the network once, and then let the server admins worry about capacity and VM placement and a whole bunch of those things. The third important point is what we've built is a scalable layer 3 solution. We believe layer 3 is critical, layer 3 mobility is critical in talking to our customers because most of them have layer 3 networks. They don't have just layer 2 networks. And the advantage of solving the problem in layer 3 is it lets you handle both layer 2 and layer 3 as the physical network, right? We are not constrained at all. So the fact that this solution is immediately deployable means you can get more from your investments today. And as I said earlier, we can support any kind of hierarchical and flat network topology using network virtualization. Now, let's not forget, at the end of it, this is not just a concept, right? What we have really done here is we have made it really easy for customers to onboard workloads to the cloud, right? The reason why it's easy is because, as Yushin demonstrated earlier, you don't have to change a whole bunch of network policy and network infrastructure, do IP renumbering and all of that to move your workload to the cloud. So by making the move seamless, we think that it's going to improve cloud adoption. So again, in summary, we'd love for more partners in the GRE ecosystem. We want you to build management software that's multi-tenancy aware. And as I said, because the multi-tenancy aspect is sort of fully integrated into the product and in the packet in the wire, there's a whole bunch of rich services that you can build on top of the network virtualization. These are the related sessions. I'll leave this on later, but I wanted to show you the link for the informational RFC. Please read it, send us feedback, and we are looking for more people to join the partner ecosystem. There's a lot more work to be done, especially on the policy distribution side, so we'd love to talk to people about it. Thank you. We have time to take questions.